So let's go ahead and continue talking about our Bronsted-Lowry acid-base behavior. And so the goal here is to think about some species that can behave as both an acid or a base. And so we're looking at H2PO4 minus and HCO3 minus. And the idea is if you're talking about its conjugate acid, it's acting as a base, which means it's gaining an H plus. And if you're talking about forming a conjugate base, that means it acted as an acid, and so it lost an H plus. And so its conjugate acid would have one more hydrogen, so it would become H3PO4. Again, it's now going to be neutral because it's gained a positive charge. Its conjugate base would have one less hydrogen, so instead of 2, now it only has 1. Still PO4, instead of 1 minus, it's now 2 minus. The same thing's true for HCO3, right? It goes from HCO3 minus to H2CO3, and from HCO3 minus to just simply CO3, 2 minus, when it becomes a conjugate base. And so these conjugates look very similar, and so that's what you're going to need to rely on when it comes to looking at Bronsted-Lowry reactions. And so the first thing that you want to do when you look at a reaction like this is you want to find the conjugate pairs. Again, they are very similar, so those two go together, these two go together. And then what you want to do is you want to look at the pair. The species with more hydrogens is the acid, right? So if you're comparing C2O4 to HC2O4, HC2O4 is the only one with hydrogens, so it's the acid. This must be the base. Likewise, CH3COOH has an extra hydrogen than acetate CH3COO minus, and so this must be my acid in this pair, and this must be the base. Now, there's several ways to look at this. One of the things I want you to recognize is the pattern here. Within each pair, there's one acid, one base. On each side of the reaction, there's one acid, one base. And so you can use that pattern to make sure that you are correct. The other thing to realize is, right, that you are simply moving this hydrogen from our acetic acid onto our C2O4. That's the only thing that's happening in this reaction. So again, acid-base reactions are relatively simple, right? We're just moving an H plus from an acid to a base. And so in the forward direction, our acid on the left-hand side is our CH3COOH, and it's becoming CH3COO minus. So again, it's acting as an acid. And then the acid on the product side is our HC2O4 minus, and it started off as C2O4 2 minus. But again, that's the reverse direction. That this would be the acid going in the reverse direction, giving a proton to the base. Now, let's look at our second example here. Again, NH3 and NH4 are a pair. HCOO and HCO minus is a pair. And so this is the acid. It has an extra hydrogen compared to this one, which is the base. NH3 is the base, and NH4 plus is the acid. Again, it has more hydrogens. And so my two acids are HCOOH on the reactant side, NH4 plus on the product side. The base in the forward reaction, or the base on the product of the forward reaction, is HCOO minus, and the conjugate base of my product acid is our NH3 minus. So again, recognizing what the acid and the base is a good way to kind of follow what's happening in this type of Bronsted-Lowry reaction. Now, there is an exercise that looks like this, so I want you to take your time and work through that, and let's move on to our last page.